Welcome back to Physics with Miss B. And I have a little surprise for you. We're going to be doing paper 2 for May, June, July 2021. So let's start with question 1. It says, state Hooke's law. Hooke's law states that the force applied to the spring is proportional to its extension, Vmax. So you just had to know that. Then section B, you had to actually do some calculations, or you could have done some pattern calculations without knowing what you had to do. For instance, the question says to determine the spring constant or stiffness of a spring, a student placed different masses M on a hanger that was attached to a spring and recorded the length of the spring. Table 1 shows the mass and corresponding values of length. So we have these right here. We familiarize ourselves, and then we had to fill in 4 spaces under the force column. And if you look at 0.1, you realize it becomes 1. So you just follow suit. You just go, well, that comes 0.1. We're going to just make 2, 3, 4.2, and 5. And then we're going to have here the extension. How to get the extension? Well, if you look at 70.2, you realize that that's the original length of the spring. 70.2 is the original length of the spring. And I'm coming. So 70.2 is the original length of the spring. So maybe I could put that right here. That's the original length of spring. And you'd realize that when you go down, when you add the 1.0 Newton, you're going to realize that the length of the spring actually increases by 4.2. That's the extension, right? So this would be the length. The length would be the extension added to the original length of the spring. And if you keep going down, you realize that, well, now it's 79.2. But remember, if you have the original length of the spring, you could always work out the extension by subtracting the new length, by subtracting the original length of the spring from the new length of the spring. And that will give us 9, right? So in other words, to calculate column 4, you would say new length of spring minus the original length of spring. So original length of spring. So that's the calculation for column 4, and you will end up with 9.0, 13.7, and 22.5. Okay? So here's another thing for you to realize this if you don't know what to do for this one. If you ever use a spring balance, you would realize that every time you add 100 grams, you would see that it will be equal to 1 Newton. Then increase. If you do 200 grams, it will be equal to 2 newtons. So if we know 100 grams is equivalent to 1 Newton, then if you convert grams to kilograms, we know that 0.1 kilogram is equivalent to 1 Newton. So therefore, 0.2 kilograms will be equal to 2 newtons, 0.3 kilograms, 3 newtons. So you're just moving the point back 1. Okay? And how do you convert grams to kilograms? Well, we know that 1 kilogram is equivalent to 1,000 grams. And so we put the grams on the same side as grams here, and put x. So x would therefore equal to 100 grams times 1 kilogram divided by 1,000 grams. And what we do get is a tenth, which is 0.1 kilograms. All right, so that's how you do it. So I'm just giving you some extra help along the way. So once you have your points, the next question says to complete table 1 by inserting the missing force and extension values in the columns 2 and 4 respectively, which was for 4 marks. Okay, that's cool. We did that. And so now we move on to question B2. It says, using the grid provided by figure 1 on page 5, plot a graph of extension E versus force F. So E against F. I already went ahead and plotted the graph, so you will end up with a straight line graph right there. A nice straight line graph. And I calibrated the y-axis, the extension, the y-axis in multiples of 2s, because sadly, well, if we look at the range over here for extension, you realize it actually goes from 0 to about 23. But to our dismay, they only have 21 lines here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 lines. So obviously they don't want us to use a 1-to-1 scale. Here, 1 centimeter to 1 centimeter scale. They don't want us to use that 1, 1, 1, 2, 3, 4. They want us to use a different scale to make our plotting kind of a little difficult. But like I tell everybody, plotting doesn't become difficult once you know what each point is equal to. So I'm going to show you how to calculate the values of each of these points in here. Well, what one would equal to, because these are equal increments. So let's go with 4 and 2. So you always subtract the smaller value from the larger value, and you will say, well, 4 minus 2, and then you count the spaces. So in between here, there are 5 spaces. Count 1, 2, 3, 4, 5. You don't count the lines, count the spaces, and you divide by 5. And so you're gonna end up with 2 over 5. Okay, and so each space will be equal to, I'm thinking 1 over 5 is 0.2, so a space will be 0.4, right? So if you calculate that, it should be 0.4, right? So each space, each line now is 0.4, so this will be 2.4, and this will be 2.8, and you just keep adding 0.4, 0.4 going right up. Okay, and then in here is much easier because we have 10 spaces in between 1 and 2, so we minus 1 from 2, and we end up with 1 over 10. So let me do it correctly. So let's say 2 minus 1. So so this is for this, and then let's say for here is for here. And once we get this going, we have 1 over 10, and that'll be equal to 0.1. So each point here is equal to 0.1. So this will be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1. So yes, that's how you work it out. And then you just plot accordingly. You just go over here. They told us what to do. So our plottings will come from extension against force. So we put an extension on the y-axis and force on the x. Force is very easy to plot because, I mean, it's 0, 1, 2, 3, 4.2, and 5. Very easy. This is the one you had to look out for and to be careful. But you're supposed to receive a straight line graph, and this straight line graph indicates that this spring was indeed following Hooke's law, which means that once you remove the masses or the forces, the weights from it, what would happen is that the spring will recoil to its original position. So this spring exhibited Hooke's law very well, which shows that as number 1 states, the force applied to the spring was proportional to its extension. All right, then of course the next question is going to be to solve for your slope. And what I do with my students is that I tell them to find 2 points that you didn't plot along the line that you would have drawn, the trend line that you drew. Find 2 points. So I have my 2 points here, which you can see, an X and an X down here, to look a little different from the actual points that I would have plotted from the data. And once I get my X's, I find the X's X and Y coordinate, and I number this one 1. So this will be Y1 and this will be X1. So we have the Y values, you just come across here, so you get that, and the X value come down here. And so what I did, I tried to make sure that I was on obvious points and points that were easy to plot. So I try not to fall between a space or anything like that. I want to fall on a cross here, and by cross here I mean like where 2 lines intersect or cross over like this. I don't want to be in a space like this, because then I'll be guessing all over the place, right? So I don't want that. All right, so that's that for finding the values for Y1 and X1. And then we have to find the values for Y2 and X2. So again, I try to plot like obvious points. I try to, put a X on obvious points. These points on the Y-axis are very obvious. And once we fall on a line and not a space here, this too will be obvious or easy to calculate. And I ended up with 0.3 for X2 and 1.2 centimeters for Y2. Please note you have to use your units, otherwise the calculations will become difficult, so you need to know where you're going. Okay, so once you listed your units and your values and everything on top of your page, now you know where you're going, and you could go and just stick them into the equation used for solving gradients, because they now ask us for the slope, which is another word for, well, that's for the gradient, which is another word for slope. And so we say S is equal to the difference of Y over the difference of X, which would be Y1 minus Y2 over X1 minus X2. If you did Y2 minus Y1 over X2 minus X1, it's the same thing, you can get the same answer, okay? Just that maybe your values would be negative, and we all know negative divided by negative gives you a positive number. Once you substitute your little numbers in here, you're going to end up with 4.467 centimeters per newtons, or something very close to that, but they usually have a range which they work with. And so yeah, so hopefully we got that number together. Let me know in the comments below. Then from there, you're given the gradient, which is S is equal to 1 over K. Calculate the spring constant for that. Well, let's remember that to find the spring constant, you use F equals to Kx. And now they're asking us to solve for the spring constant. So if we had this original equation to solve for the spring constant, which is this right here, this body right here, it'll be K equals to F over X. And as we can see here, this is telling us to solve for K, and we see that K would be equal to 1 over S. If you look up here, you'd realize that S represents extension over force. This, by the way, means extension, and this means force. Okay, let me spell it out for you. And so once we put K, we say, well, K in this case is equal to 1 over S. If we substitute, we'll have k is equal to 1 over x over f. And voila, look at this. If you divide by a fraction, you always flip it and you will end up with f over x. And we get back our equation up here, which is k is equal to f over x. So that's how they get this done. So sometimes we don't know where we are going, we don't know if we're using the equation, but I just felt like for good measure just to add this so you can see why they said s is equal to 1 over k. And so since we already calculated s, we just put we substitute s for 4.467 and we put back our units. And once we calculate, we realize our answer would be 0.2. And since we have a fraction beneath the 1, we can flip it. We have 0.2 newtons per centimeter. Then they say, well, given that f is equal to the constant times the extension, find the length. Please be careful asking for length and not extension. So they said when the force of 8 newtons is applied. So again, given that f is equal to ke, calculate the length when a force of 8 newtons is applied and assume that the spring obeys Hooke's law. Okay, so we're going to list everything that we have or we are given, and we have force at 8 newtons. We already found out what k was, and so we're going to just substitute again. We're going to solve for the extension, right? So we see E will be equal to F over k, and putting in our numbers to substitute for k and f, so k and f, we get 40 centimeters, because this again, if you like, I will show you, it would be n times centimeters over n. So this unit gonna flip and multiply by n, and they will cancel out. You end up with centimeters. That's why I say use your units going throughout, otherwise you're gonna be lost. But then if the original length of the spring is 70.2 centimeters, and the length of the spring, the new length of the then the new length of the spring with 8 newtons attached to it is going to be 70.2 centimeters plus the 40 centimeters. That's the extension. So we need to figure out the length altogether when you add on that 8 newtons, okay? And it makes sense. 110.2 centimeters with 8 newtons. If we go back here, we have 5 newtons at 22.5. So therefore, it should be bigger than 22.5, right? It will make sense because this is, suppose it's still following Hooke's law. So we see here that 1 newton represents, okay, so 1 newton should represent an extension of 4.2 centimeters. So therefore 8 newtons should represent x, and so if we multiply, because our x will be equal to 8 times 4.2 centimeters. I know the newton's going to cancel out. Let me just put it there so you can see, divided by 1 newton. And if you multiply 8 by 4, 4.2, you get 33.6. So based on calculations in theory, we should have an extension of 33.6 centimeters. But which is very close to our experimentally determined value of 40 centimeters, pretty close to 33.6. So yeah, so we're good to go. That's really good. And plus we kind of rounded up here, and yeah, we rounded up, so that would account for some changes in the length, but we are good. Let me know what you got on your test, but you should get 110 somewhere around there, because if we, let me go back now, if we added, if in theory, if we added 33.6 to 70.2, in theory, the length would then be 70.2 plus 33.6 centimeters. In theory, should give us 33.6, 103.8, 103.8 centimeters, which is off by not a lot. So if we subtract 110.2, off by about 6.4, not that much. So let's hope that falls in the range for CXC. And let's hope that we all had a number that's similar. But don't stress, don't fret. If you didn't get these answers, I hope that you just moved on, because there are other questions that could be answered. So, and you still have paper one. You still have paper one. Okay, so now we move on to question 2, where it says, define each of the following terms. Sorry about my cough. I usually have this pestering cough when I'm very excited. So here goes. So moment of a force. The moment of a force about a pivot is the product of the force and the perpendicular distance of its line of action from the point where t equal to F times d. And this, of course, is you didn't have to write it in exactly these words, but once you knew the equation, you could have just said the moment of the force is equal to the force times the perpendicular distance to the point where it's acting. You could have write something like that. Very, very student-esque kind of response. Anyway, so moving on. So center of gravity. Define that. So the center of gravity of a body is the point through which the resultant gravitational force on the body acts. So basically acting, usually if it's uniform, it's a uniform body, it's acting to the center. Then it says state the two conditions necessary for a body to be in equilibrium. It has several low center of gravity, wide base, and larger weight, right? So to increase stability. Okay, so now we are on to moments, and they didn't bring a pivot like drawing, but it can represent a pivot. We can actually make it into what we usually see in the book, and we see over on the next page just now. So figure 2 shown below is a diagram of a non-uniform wooden plank. Usually we have uniform planks. AB, which is 2 meters long and weighs 1,000 newtons. The plank is supported from a ceiling by 2 vertical springs, P and Q. The plank is attached at a distance of 0.5 meters from each end. C is the center of gravity as shown in figure 2. Then it says when the plank is horizontal, the tension on spring P is 600 newtons. Calculate the tension on spring Q. Show all working. So with this one, we're going to do sum of all forces is equal to the sum of all downward forces. So P plus Q will be equal to W, right? And so since P is 600, we substitute P for 600 newtons, add Q, and W, of course, would be the weight of the plank, which is 1,000 newtons. We perform a simple transposition where we subtract 600 from this side, and we just subtract 600 from this side, and we have it right here, just showing you the operation. And because this would go, and then you would end up with 400 newtons, so Q would be 400 newtons. So the next question now, it says, this is me drawing the, this is my representation, schematic representations of how the drawing would look in an exercise book or textbook, most of textbook. And you wouldn't have the springs that, to psych you out. So it says, by taking the moments about A, determine the horizontal distance from P to C. And P to C is from this. So this is actually P. I put a P up here. Let me put it here so you could see it. So from P to C. Okay, so if you take the moments about A, that means the pivot is going at point A, and everything gonna be turning according to where the pivot is. So what I usually do is I list out all the forces that will be anti-clockwise. ACW stands for anti-clockwise, and all the forces that would represent clockwise moments. Now, here's a little tip. Whenever you have a pivot, this force and this force will be moving anti-clockwise, right? And then this force, so let me put another color. This force and this force will be moving clockwise. Or what I would tell people to do is to place the rubber end of the pencil by the pivot and just push it according to the force. So if you have a pencil here and you put, let me see if I could do it. Let me come out and show you what I mean. So if I just imagine I'm going to insert one line, and the line, let me put it with an arrow and let me put it across here. So let's just imagine the arrow is a pencil, right? And let me darken the line so we could see it. Darken it. I mean, I could give you all the answers straight, but explanation is key. So you could see where it went wrong. So say I put it as green. Let's hope that this moves how I want it to move. So if you want to look at the force P, right? This is P right here. You put your pencil at the tip of the pivot right here, and you move the other end like this. So you see that it will be going in an anti-clockwise fashion. Now if I want to see where C is going, the tip stays there. And remember, it's always the distance from the pivot, okay? And I will move it. So this will show me that it's going in a clockwise fashion. Now if I extend it out here and I want to see where Q is going, I will see that Q is going this way, anti-clockwise. And as you can see in the picture, I labeled them. So you could see here is 600 times 0.5. So 600 is 0.5 meters away from the pivot. And then the 400 newtons, where is the 400 newtons? So 400 newtons would be 1.5 meters away, because remember on the picture before it was 0.5 meters away from the edge, and it told us that the length of the plank is 2 meters. So you just subtract 0.5 from 2, which will give you 1.5, and those will be our anti-clockwise moments. So that is why I always label my forces in the direction they're going. And since it's at equilibrium, we can therefore say that anti-clockwise moments equal to clockwise moments. So therefore 1000 is the only one going in the clockwise direction. So therefore it will be 1000 newtons times x. So once we find the distance of C from the pivot, we would realize that we could solve for the distance PC. So 600 times a half gives you 300 newtons. And then we have here, so 600 times a half gives you 300 newton meters. 400 times 1.5, as you can see here, will give you 600 newton meters. And then 1000 newtons times x will give you 1000 newtons x. So you add the 600 and the 300, you get 900, and then of course you divide both sides by 1000. X will be equal to 0.9, which says that it is actually exactly as it is, because usually you would see in pictures that the weight of uniform planks would be in the center, snap dab in the center. So this would have been like 1 meter away from the edge A and 1 meter away from the edge B, but it's not uniform. So the center of gravity, or the weight of the plank, is situated a little closer to P, which we're going to answer later. So here we have our x, and once we find the distance of x, we can, knowing that this is the distance here of the pivot A from P, we could solve for this distance in here. So we just say, well, hence the distance from P to C will be 0.9 minus 0.4, and that will give, 0.5, and that will give us 0.4 meters. That was for 5 max. So if you tried something, you could get a little 2 max, 3 max here and there. That would be nice. But I hope you understood what I meant. So anytime you have your pivot, you place your pencil at the rubber end of your pencil here, and you pull it down or up according to what direction your force is acting. And if you had forces over here, you could do the same thing to determine whether something is clockwise or going anti-clockwise, right? Then it says, state why the center of gravity is located closer to the point P than the point Q. Well, because P is a stronger spring, probably could hold more, and the plank, the actual answer is that the plank is not uniform. Okay, 1 point. Tell me what you wrote, right? Tell me what you wrote if you had something different. Now we're moving on to question 3. Question 3 is about waves, and they say waves can be described as transverse or longitudinal. Explain what is meant by transverse. So we're going to be dealing with light. From the time you see transverse, we're going to be dealing with light, and we know a transverse wave does not require matter to travel. It travels at a speed of 3 times 10 to the 8 meters per second. In a vacuum, and transverse waves reflect, refract, and diffract. They have vibrations that are perpendicular to their direction of propagation. I tried to give 3 lines in this case because I knew so much, so I felt like a little showing off. So maybe you would have had this line, and it might have worked because they only asked what is meant by a transverse wave. They didn't ask to give properties, but I just went on because I knew they were correct. But yeah, and they said, now give one example of a transverse wave. Well, visible light waves, all light waves. You could have written that. You could have written microwaves. You could have written radio waves. You could have written any of the types of radiation that we know make up the electromagnetic spectrum. Gamma rays, X-rays, anything. So define the term ultrasound. This is a sound. This was a question that I don't usually see. And to tell the truth, I would have made up something because it's not something that I would be like, yeah, I know. But you try. And so the actual answer is this is sound that has a frequency above 20 kilohertz, right? And then the other one will be infrasound. That's the one below 20 hertz. I'm not sure, just look it up. All right, so B2, it says state one example of the application of ultrasound. Well, I put 3 just in case you would have had others, but the major one that we all know about is the one that's used in medicine to view unborn babies in the mother's womb. So that's one. We could say that is used to measure distance by bats to determine where they are, right? And then we could talk about dolphins using ultrasound to communicate. Okay, so it was only 1 mark, but $1, one of anything adds up. Then they went and brought something that I saw on a 2000 paper, but it was a little less intense. So we see here that we have an incident ray hitting off at some boundary mn towards the normal, and then we have some refraction, and this is the ice cube, by the way. We have some refraction happening in here, and the refracted ray then becomes again an incident ray to the inner boundary NO of the ice, right? And we see that the light the light goes along the boundary, right? From the time the light that is incident to the boundary goes along the boundary, we already know this is the critical angle, and that's going to be a question that's coming up, and they told us to label it as theta c, so just heads up. But first off, let's deal with the angle of incidence. Oh well, let's read the question first. So figure 3 shows the path of a light ray from here through an ice cube along along with two rays showing partial reflection. And okay, they said to determine the angle of incidence on the face MN. Now, a lot of people tend to make the mistake and say the angle of incidence is between the incident ray and the boundary. That's incorrect. The angle of incidence is always between the ray and the normal. The perforated line is the normal, okay? So if you made that mistake, now you know. So to find that out, the normal is always perpendicular to the boundary, and so that means it will have an angle of 90 degrees. It's a right angle, so you would subtract 31 from 90 and you'll get 59 degrees, okay? Then from there you're asked what would be the angle of reflection. If you know your reflection laws, you will know the angle of incidence should be the angle of reflection, right? And so the angle of reflection would be 59 degrees. It's 1 mark. And now we have the angle of refraction at the face MN, given that the refractive index of ice is 1.3. So they want the angle of refraction. So this is the equation that you would use. It would be NA over NI. Now A stands for air and I stands for ice. So this is the refractive index of air over the refractive index of ice divided by the sine of the angle of ice over the sine of the angle of the sine of the angle of the incident ray in air, right? So it sounds like a lot of la 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 la, but there is an equation for it. So if you ever have a refractive index X over refractive index Y when you're dealing with air, well, when you're dealing with anything, whatever you have on the next side, right, would be switched. So in the case of an angle, this would be Y over sine theta X. So everything corresponds to this statement, because you could also use this to find speed if you have the index and the speed of X. You could use it to find, I think, frequency over frequency X. A lot of things you could use it for. I just can't remember. There was a fifth one, but let me see, it was sine, speed, frequency, and something else. Anyway, you could check your text. So once you have all of these, so once we have A and I A on top and I on the denominator, whatever we're looking for, we're gonna have to switch, right? And so I listed out what I have. We know the refractive index of light in air is 1. It's always 1. And so whatever light, so when we look, so the light that was passing through the medium air will correspond to this refractive index, would be 59 degrees, right? So that will be written right here. And then they gave us the refractive index of ice, and now we have to look for the angle of which one is I, or the axle? The angle of refraction within the ice, right? So once we go there, we say we put our numbers accordingly. So 1 over 1.31 equal to sine of x, which is theta 1 over sine of 59. So be careful, make sure you list these things out, and then we're going to find the inverse of sine. So this, when you want to find this, it's going to be sine 59 times 1 over 131. And because we just want to find x, we're going to make it inverse of sine, because we want to get rid of this sine that's going to be left there. And we're going to end up with 40.9 degrees. So let's hope that everybody got that. Okay? So if you're still confused, let me just do this for you, where we'll put, I'm going to do the cross multiplication for you. So this will be 1 times sine of 59 over 1.31 equal to sine of x. And then the next thing we'll do would be this would be now the sine, because we need to get rid of the sine. We're going to have just x is equal to the inverse of sine, and then the rest is history. And then the last thing is, on the diagram on figure 3 on page 11, label the critical angle theta c for ice. And critical angle again would be that angle at which there is no light leaving the boundary. So no light left here. All the light was running across the boundary here at a 90-degree angle towards the normal, which indicates that this is the angle, the critical angle. Once the critical angle has been surpassed, then you will have total internal reflection. Okay? Alright, so that's that for this question. Okay? Now we're on question 4. On figure 4 below, sketch the graph of pressure versus temperature in degrees Celsius for an ideal gas. Now, you didn't have to do this other part over here. I just did it so that you can see what I meant from this explanation here. They want you to just draw the line going here, and for pressure in atmosphere versus temperature, 2 marks. So you had to label your axes and draw the line. I would have said label your axis to get your little 1 mark, and then you draw your line. And if you remember, the book would always have this drawing, especially for ideal gases, for pressure against temperature. And if you didn't even know, the question gave it away. It said, explain how the graph could be used to derive the Kelvin scale. Hello. So, not to sound like that, but if you were familiar with the chapter and you didn't know what the question was asking, a little light bulb might have gone off at some point, because to derive Kelvin, they have not found out exactly. They have never, the tests that they have done have never proved that the absolute temperature is actually negative 273 degrees Celsius. But they have done experiments that have produced pretty close results, about maybe here, but never to the actual result. So what they did is that with all the results they would have accumulated from doing different temperatures at very cold, from doing different experiments at very cold temperatures, they found the best fit line, and they just extrapolated across here and extended the x-axis. And what they found was that absolute zero actually hits off at negative 23 degrees Celsius, better known as 0 Kelvin. And that's what they did. Then the next question was, using T to represent the Kelvin temperature and theta to represent the Celsius temperature, state the mathematical relationship between the Kelvin and Celsius temperature scales. Well, once you have degrees Celsius, to convert to Kelvin, you have to add 273. So that's what they were asking for. Yeah, so they wanted you to like demonstrate how you would have calculated it, and this is the relationship in actuality. Then they ask us a little pressure, they ask us a question involving the variables volume, pressure, temperature, keeping the mass of the gas constant, and you were supposed to find V2. So like I said, in all my things, so that you could keep your sanity, you want to list everything out. right? And it says a container stores 5 cubic meters of gas at a pressure of 13 atmospheres and a temperature of negative 23 degrees Celsius. Calculate the volume that the same gas would occupy at a temperature of 23 degrees Celsius and atmospheric pressure of 1 atmosphere. So I listed my V1 as the first one that I had, and whatever corresponded with V1, which was the pressure, P1 would be 13 atmospheres. So 5 cubics, well, I have the wrong unit right here. Oh, see, even I make mistakes. So this is meters cube. So easy fix because I have it throughout, so I could just get rid of it. But it's easy fix because it's the same number. So 5 cubic meters, 13 atmospheres, and then don't forget that whenever you're doing these calculations, especially for gas laws, you need to convert your temperatures to Kelvin, so you have to add it to 73. Hence the little hinty question over here. This was a little hint. This test was actually a fair test, and I hope that CXC follows this trend forever, because I think this was within your understanding. It didn't go over your head. And so you just had to remember these little things. If you didn't, I'm pretty sure they have something in place where they might minus 1 mark for that little mistake, and then they're going to give you marks for your execution. So P1 V1 over T1 equal to P2 V2 over T2. And again, so this, and this were listed, and then they said to calculate the volume, which was V2 X, we need to find the volume of the same gas would occupy a temperature. So we have temperature here 27 degrees Celsius, and the atmospheric pressure is 1 atmosphere. So we list them all out, and then we write our trusty equation. Once we have V, P, and T, we know it's P1 V1 over T1 equal to P2 V2 over T2. So therefore V2 will be equal to, just move this up like that, because it's only multiplication and division we're doing, there's no addition in here. And move the P down, and yeah, so you move it like that, and then we're left with V2, and we substitute all our numbers in here, get rid of our units that we can get rid of, and we're left with our meters, cubic meters. And once we do the calculation, we should end up with 78 meters cubed. Okay, makes sense, because remember, at a hotter temperature the gas should take up more volume, it's going to expand. This was really cold, this was negative 23, so it's going to be condensed. So at a hotter temperature it's going to start to, expand and spread out. So this makes sense, the number makes sense. Okay, see now, blocks X and Y in figure 5 are identical except for their temperatures. So block X is a higher temperature than block Y, and so let's explain the difference in the motion of the particles in block X compared with the motion of the particles in block Y. And the hotter the block, the more the particles are going to be vibrating. So particles in block X are vibrating much faster than particles in block Y, since they have acquired more heat energy. Something like that you could have write. And then it says, in which direction would thermal energy be transferred? Remember, heat moves from higher temperature, from something with higher temperature to something with lower temperature, or higher heat energy. Something that has more heat energy to something that has less heat energy. That's how conductors work. With thermal conductors, you heat up one end, and the heat moves from the area that has high heat energy to areas that have a low heat energy. So something like that. And so we have it here. So thermal energy would move from X, the higher temperature, to Y, the lower temperature. And it says, state the condition under which the transfer of thermal energy would cease. Well, it would cease once you reach thermal equilibrium. Did I write that here? Yeah, so once block X and block Y equal the same temperature, they would have achieved thermal equilibrium, hence transfer of thermal energy would cease, because it would be the same temperature. Okay, so that's what we're looking for, that's 15 marks. Now they bring the nice motor, and I like the fact that they drew it in 2D format. This was nice, nicer than when they have it in 3D. 3D used to set me off, and I think as a student, I think children used to get intimidated by it. So something simple like this, on a nice flat view is nice. So it says figure 3 shows a simple DC motor, so we need to take note that there's a motor, not generator, which consists of a coil of wire A, B, C, D between the poles of a magnet. The dotted line represents the axle about which the coil can turn. A current flows through the coil in the direction shown by the arrows. And that's the thing, when you're dealing with when you're dealing with motors, when you're dealing with that, they always give you the direction of the current, and if you don't get the direction of the magnetic field, it's understood that the magnetic field always travels from north to south. So it says draw the magnetic field between the poles of the magnet on figure 6, and that's what I did. I drew my magnetic field line going from north to south, and then I drew the other two to just make it complete. And so that will give you 2 marks, right? So if you knew that, you could have show off. And then now it says state the direction in which side dA of the coil will move as the coil starts flowing through the circuit. So it will move north. So you had to use your 3 fingers on your left hand, which would have been your thumb, your index finger and your middle finger, and you could label them FBI. F would stand, so let me see if I could draw it here. I was trying to make a video. I did make the video, but it's not allowing me to send. So let's just say you have your thumb, and then you put your index finger like that, and then you put your 3rd finger like that, right? Your other 2 fingers, they're insignificant. Let's me trying to draw. And so we have our hand right here. So I would tell children, label your fingers F, B, I, and you can remember it like that because you know the FBI. And then F would stand for force. This would be the force, as in the thrust. And the B would stand for definitely the direction of the magnetic field lines. So direction, I forgot the word, direction. And then you will have this will be the direction of the current now going this way. And note well that all of these are at 90 degrees to each other, right? So the direction will be going this way, and this will be direction of current. And now that you have your guns up on your left hand at 90 degrees, what I want you to do is to put your 3rd finger in the direction of the current in the AD line. That's what they said I wanted it, in the DA line. So you're using that line, and you're putting your 3rd finger in that direction, and then you're gonna put your your index finger in the direction of north to south. So you're gonna turn it north to south. So you have your current, and then you have your north to south, right? So your fingertips show the direction, and you would realize, so we have here, if you turn your hand in that direction, you're going to realize that your finger is going up north. Okay, so that is how it will look, and I wish I had a little video. Maybe if I try again, I'll try. So north or up, and then it says name the rule used to determine the direction in which side dA of the coil moves, and the rule is called Fleming's left hand rule. So you had to use the left hand. So when you're dealing with motors, you always use the left hand. When you're dealing with generators, you use your right hand. Okay? Alright, so then now it says explain why a split ring commutator is used in a DC motor. Well, split rings are used to maintain rotation. And the split ring is fixed to the axle and allows this rotation to happen by switching connections between the coil and the battery every half revolution as it rotates and rubs against the fixed graphite brushes, better known as contacts. So I hope this was sufficient enough for 2 marks. Okay, so now we on to this trusty little fellow. And it says figure 7 shows a graph of the variation of voltage with time across the output terminals of an AC generator. So now we're going on to generators. And it says calculate the value of the frequency for the generator. Well, you could use 2 things. You could use frequency is equal to 1 over period. And we'll see that you take 1 full cycle, which would be a full on crest and a trough. And it ends at 0.02. And you will get 50 hertz. Or you could reason it out, like if 1 cycle is produced in 0.02 seconds, we know a frequency is considered to occur when, how many cycles pass in 1 second, and that is a frequency. That's what we consider a frequency, how many cycles pass in 1 second. So therefore, for me to solve for frequency, knowing that little definition, I would say, if 1 cycle passes in this amount of time, how many cycles pass in 1 second, which represents frequency, right? And so this would give me the same 50 cycles per second, hence 50 hertz, the same thing, right? So to me, once when you could work out things 2 different ways and get the same answer, pretty much you're on the right track. Then they said the peak voltage is applied by the generator across 100.0 ohm resistor. Calculate the peak value of the current in the resistor. Now the peak, if you go back, the peak is at 200 volts. Okay, so let me see, did I do it right? Yeah, so I listed out what I had. I was like volts equal to 200, and they give us the resistance equal to 100 ohms. So they're asking for current. We see something familiar, Ver, and so we said V equals to IR. So therefore, I would equal to V over R. And we have our things that always a list out because we want to keep our sanity. Don't just write things haphazardly, okay? So 200 volts over 100 ohms will give you 2 amps. Then the generator is subsequently rotated at twice the frequency in B2. State the effects this will have on the period of the output. Well, the period will now be 2 seconds. Well, this is what I got. If it's 50 hertz at 1 second, then 100 hertz would occur at how many seconds, right? And I got the period. Period is time, so then the time will be 2 seconds, right? Then it's the value of the output voltage. They never mentioned anything. They didn't mention that anything changed. It's 1 mark, 200 volts, right? Right. Then we have radium-226 is radioactive and is represented by the nuclide 22688 array. And so for a neutral atom of radium-226, state the number of protons. Well, the atomic number represents the number of protons in a neutral atom, meaning an atom that has not reacted yet with anything. So we write back 88, and it also represents 88 also represents the number of electrons. So 88 will go for these 2 questions right here. And then they say, what is the number of neutrons? Well, you would subtract 88 from 226 because 226 is a mass number. This is a mass number, and the mass number is the sum of the neutrons. So number of neutrons plus the number of protons. So you're just subtracting the number of protons from the mass number to solve for the neutron count, which comes up to 138. Then it says a radium-226 nucleus decays by beta particle emission to radon. And so what is meant by the term radioactivity? Well, it is a spontaneous disintegration, decay of unstable nuclei. So that would be enough. If you wanted to be like, for example, examples of radioactive substances are nuclei include uranium-235, carbon 14. That's if you want to go on and on, but only ask what is meant by that, right? And you could also add you could probably add disintegration occurs with the radiation of what do you call it, lost my words, but with alpha, beta, and gamma, or gamma and radiation occurring. So you could write something like that, like, this happens due to the release of alpha, beta, or gamma radiation, something like that. Now it says complete the equation for the decay of radium-226. So the torus is an alpha particle, and once we know alpha particle is a helium particle, we say 4 to 2, and we just make sure whatever is here would add back here, because is an equation, is an expression that should add back. What you put in should come back. So if you have 88, 2 plus what gives you 88, that would be 86. You have 226, 4 plus what gives you 226 would be 222, and we have radon. Okay. That would have given you 2 max. Alright, so we're on the last leg of the race, and we're at question C, very last paper, and we have radium-226 has a half-life of 1600 years. Define the term half-life. So it is the amount of time a radioactive sample takes to decay to half the amount of its original amount. Right, so it's the amount of time a radioactive sample takes to decay to half the amount of its original amount. Okay? So in other words, let me see if I could draw it out, because sometimes the definition can get a little confusing. So suppose you have an amount of sample, and you have this sample here, and let's just make this represent our 8 times 10 to the 8 particles. And so it tells us that it takes, so this is going to be our starting point here, and it tells us that from 0 years to 1600 years, it's going to take that amount of time for it to be half the amount, of what it originally was. So now it's 4 times 10 to the 8. And it's going to take another set of years, another 1600 years, to be half this amount now. So this is going to be the new original amount to the next amount that's going to be the original amount. So it's going to take another 1600 years for it to decay. And this will be, year 0, 0 year 16. This is after 1600 years. And this again, if you add 1600, this will be coming to the second question. You get 3200 years. Okay? And so forth and so forth. So in this question it says, at a certain time, a sample contains the 8 times 10 to the 8 radium nuclei. Then it says, calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years. So just like how I drew it here, right? Maybe I should draw the arrows smaller and then, just use this. So let me draw the arrows smaller, because you get the concept, you get the idea at this point. So I'm going to draw the arrows shorter and try to fit everything in it. So on the 1600 year, we're going to have only 4 times 10 to the 8 left, right, particles. Then on the 32nd, so we're just adding 1600, because every 1600 years this substance breaks down by half. It breaks down by half. Okay, and so we're gonna have here again, this is gonna be the half, and this will be 2 times 10 to the 8, right? So that break down by half. And if you add 1600 to 1600, you get 3200. So then by the 4,800 year, it's gonna break down, this amount now gonna break down to 1. Okay, so that's how much you're gonna break down to. So the question now that we have to pay attention to, the part that we're paying attention to, says calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years. They did not ask you how much of the sample was left after 4,800 years. They ask you how many alpha particles were emitted. So this might have gone over some heads, and this is how I understand it. So I said, okay, by the year 4,800, we will have just one particle left, 1 times 28 particles left, right? So if you think about it, we started out with 8, right? 8 times 10 to the 8, and we're left with 1 times 10 to the 8 by year 4,800, right? And so this tells us, this difference is going to tell us that 7.0 times 10 to the 8 radium nuclei, right, would have been decayed. So these are the decayed particles. These have not yet decayed, as we can see here, is not yet decayed. Only when you see an arrow coming from it, we say it has half of it would have decayed. So these would have decayed. So they call these decayed particles. From these decayed particles, from these decayed nuclei, how many alpha particles were emitted? Well, what I did, remember from before, they told us that it's alpha radiation coming off, and from there we're going to have some radon, right? That will be the formation of another atom. So if we have radium, if you look at radium, right, 226 is radium 226, right? Yeah, radium 226, and we have this alpha particle coming off, and then we have ours over here, 88, says 88, and then we have 86 here, we have 222 radon here, right? We are only looking at how the alpha particles, the ratio of alpha particles to radium particles. So we see from the ratio, 1 mole of radium particles will produce 1 mole of helium particles, right? So if you go to the Avogadro's constant, if you go on the chemical level, right, you would realize that 1 mole of any substance would contain 6.022 times 10 to the 23, whatever you're dealing with. In this case, we're dealing with nuclei, right? Well, in this case, yeah. So in this case, dealing with radium nuclei. So dealing with the radium nuclei, because we need to find out how many helium gonna be left. Okay, so my rationale behind this is that 1 mole of anything will contain 6.022 times 10 to the 23 whatever. So in this case, it should be radium nuclei, right? Because the sample will contain the radium nuclei. This is my idea, because we have, in chemistry, you have to relate everything by the mole. So I'm saying, how many moles would there be making up 7.0 times 10 to the 8? Radium nuclei. Now, whatever answer you get here, right? If you calculate that, let me do it again. So if you divide 7 times 10 to the 8 by 6.022 times 10 to the 23, you get 1.16 times 10 to the negative 15. So x will be equal to 1.16 times 10 to the negative 15. Okay? Moles. So if you get this amount, right, for here, 1.16 times 10 to negative 15 moles, right? Then you're going to get the same thing here. 1 to 1, and so you're going to be the same thing here. 1.16, blah, blah, blah. So you're going to be 1.16 times 10 to the negative 15 moles for the helium. But guess what? We already see that 1.16 times 10 to the 15 is equivalent to 7 times 10 to the 8. So therefore the difference is actually equal to the amount of alpha particles emitted by the radium nuclei after 4,800 years. That is my rationale. If you got a different answer, let me know what it is you did, but that was my rationale, because this wasn't a regular schmegular question where they would say, well, how much would be left back? They ask you on the level of how many alpha particles were emitted, right, by the radium. The amount that's left back would not have broken down yet. It's still undecayed, while the rest were decayed, right? This was decayed, right? This amount. So the difference from here to here is what would have been decayed, as I indicated here. So I have 7 times 10 to the 8. So tell me what you got. Now it says, well, how much more time will elapse before the number of radium nuclei remaining falls to 0.5 times 10 to the 8? Well, since we're going from 4,800, we know we had 1 times 10 to the 8 radium nuclei left. So if this breaks down by half again, you're going to actually get 0.5 times 10 to the 8. And that, getting to this point, would only take 16, well, not only, it would take 1,600 years. And so this would be on the 6,400 year. But they only ask, how much more time will elapse, right, before the number of radium nuclei remaining falls to. So how much more time? 1,600 years will elapse. 1,600 more years, right? That is how I comprehend the question. Let me know, because I know comprehension and interpretation are very important when it comes to these examinations. All right? Okay. All right, so that's that for this examination. I hope that you did well. Please remember this paper 1, and see you around. All right, see you around. Check me out for my little physics shots. Let's hope that my computer doesn't crash again. That'd be so sad. All right, bye bye now.